Hello world and hello maths fans. Today we will be talking about sets. In the real world, when we're dealing with data, we often group it into smaller, manageable categories. For example, all of you watching this video right now could be grouped by your nationality or perhaps by your previous mathematics experience. These groupings or collections are what we refer to as sets. Today, we will begin by exploring the definition of a set. We will then look at relationships among different sets, such as union and intersection. We will look at sets within sets in the form of subsets and supersets. We will visualize all of these relationships using Venn diagrams. And finally, we will look at how to calculate the size of a given set. And by the end of the chapter, you will all belong to the set of students that completely understand sets. Hello world and hello maths fans. Today we are talking about sets. When dealing with data, we often group it into categories of... No. All right. A set, try and have a voice. A set is simply a collection of objects that share a common property. This would be a set of food items. We have some cookies, chocolate, and an apple. And this would be a set of drinks. We have Coca-Cola, some ginger ale, and some water. And we can sort items into the various sets using those properties. So here I have my grocery basket filled with various items. So I have, again, A is going to be the set of food items, and B the set of drinks. So what have we got here? We've got a can of tuna. So I think this is a food item. So I would simply say this belongs to or can be sorted into the set A of food items. I've got some chips. I would call them crisps, but we'll go with chips. They are also a food item, so they will go over here similarly in my set A of food items. We've got some juice. This looks to me like a drink, so that goes into the set of drinks, set B. I've got a banana. That's going to be a food item. What else have we got? Ooh, I've got some toothpaste. Now, the toothpaste does not belong to either set A. It is not a food item, so it does not belong to that set. And it's neither a drink, so it does not belong to set B. So I'm going to leave the toothpaste in the basket because it does not belong to either of my sets. And then the last one I've got here is some soup. Now, this one is a bit tricky. I'm genuinely unsure whether a soup is a food or a drink. Perhaps, in fact, it could be both in certain instances. So I'm now at a situation where I can say the soup is actually belonging to both set A, it is an item of food, but also set B, as it could be seen as a drink. So mathematically, we would actually say that the soup is in the intersection, the overlap between these two sets. And in fact, based on all of the items that I have laid out now on the table, we could say this is the set of edible items. So that would be the union, which you can think of as the addition in a way. It's the union of the food items and the drinks. So the union of the food and the drinks would give us the set of edible items. So I've talked there about a lot of potentially new terms. So let's go over to the screen and get down some of those definitions, just so we can make sure we're using them all correctly. So I started by saying that we could sort various items, and the idea that to belong to a set, that element or object must satisfy a criteria. And I'm going to start the transition to the screen again.
Give us 1 second, okay?
Yep. I forgot that I was going to do definition of a set. Okay. Get a quick drink. Keep the throat lubricated. So I've introduced and used many new mathematical terms there in my discussion, so let's just head over to the screen and get down some of those definitions. First of all, we talked about when an item does or does not belong to a specific set. Now mathematically, we simply write this as an element x belongs to the set A. So this E symbol here is read as belongs to. And if we have an item that does not belong to a set, we use a very similar notation, but we just put a line through the belongs to symbol to say that the element x does not belong to the set A. Now, when actually writing out the elements that are in a set, we could write them in a list, as seen here, A1 through A2, A3 through to AN. But usually we will enclose that list inside a curly bracket to signify that all of these items are belonging to and are contained in that set. When we get to more technical definitions of sets, so if we want to make very explicit what the criteria to belong to the set is, then we will often write it inside our curly bracket. So this statement is read as the element x such that x has the specified property. So it sounds more complicated than it really is. So if we look at an example here at the bottom, this particular notation will be read as the element x such that x is an even number. So 2, 4, 6, 8, etc. We then moved on to talk about the union. And I gave the example of the union of the food and the drink together would give us the edible items. Now, the way that we write this, if we have two sets A and B, is we use the symbol U, sort of telling us to be read as union, same letter, and we write this as the set of elements X, where those elements are in A or they are in B. So here, for example, that could be the element in A, could be my apple. This is in the food set, so because it is in the set of food, it is therefore in the union, the set of edible items. But similarly, I could take an item, the juice, that was in the drinks in set B. So both the apple and the juice are going to belong to the union of those two sets. It's X belongs to A or X belongs to B. Now, for the intersection, the rule is a little bit more specific, let's say. So the intersection of two sets, A intersect B, written with an N symbol there, is the set that consists of elements that are in both A and B simultaneously. So it's no longer enough to just be in one of them. You must belong to both sets to be in the intersection. And I like to think of this as the overlap between those sets. So in our example with my shopping, we saw that the can of soup, I'm claiming at least, is both a food and a drink. And so therefore, because it's in both A and B, it is in the intersection or the overlap between those two sets. Mathematically, we would write this as A intersect B equals those elements X such that, again, is how we read that straight line, such that X is in A and X is in B. So again, it must be in both of those sets. Now, when looking at intersections, sometimes the intersection will be empty. So we have a name for this when you have two sets with no overlap, and we call those sets disjoint. So we say that sets A and B are disjoint when their intersection is empty. And now here I've introduced another new symbol, which is one you'll see a lot when working with sets. It's called the empty set, this symbol here. So it's like a O with a line through it, and this will always represent the empty set, which just means the set that has nothing inside it. Now, as well as combining sets, or let's say building new sets, perhaps by adding them or taking their union, we can also take smaller sets inside those larger ones. So we can break down the sets into smaller pieces in a way. And we do this using things called subsets. So a subset is just a smaller piece of the larger set. So we have here the formal mathematical definition, but I think this is best demonstrated again with my shopping. So if we go and focus, and I'll just remove the soup for a moment. If we just focus here on our items in the food set, the set of food items. Then within the food items, I could, for example, take out the two fruits, so the banana and the apple. These are definitely food items. But I could now create a subset, let's call it C, of the banana and the apple. So the fruits, banana and apple, are a subset, they're a smaller part of the larger set of food items. So that's what we're seeing here with this notation, this sort of C contained in, it's inside the larger set A, so that's our fruit inside the food items. Now, the larger set, A, so the food items, we call the superset. So the smaller one, C, is the subset, and A, the bigger one, we call the superset. And a final thing on subsets and supersets is you'll notice with both of these symbols that we've used, we have this kind of curly C, and then underneath we have a line. Now this line is saying that these sets could be equal. It's kind of like an inequality, where we have a strictly less than or a less than or equal to. We add that additional line below the symbol, and we do the same thing here with our sets and our subsets. So if they are definitely not equal, so here the set of fruit, my banana and my apple, it's not equal to all of the food items, then it is actually what we call a proper subset. And so sometimes you'll see this written without the line to indicate that they are not equal to one another, and it is in fact a proper subset. Now, another thing that I did not mention explicitly with my shopping, but that we did see, was a property of a set, or a type of set, called the complement. Now, one example of the complement of a set would be something like the toothpaste. So when I unpacked the toothpaste from my cart, I was unable to place it in the food items, and I could not place it in the drinks items, so I kind of left it in the cart. But what I could say is the toothpaste, it's not in the food items, it is not in set A, and the way that we can refer to this is to say it is in the complement of A. So it's just saying it is not in the set A. So the toothpaste is in the complement of the food items, it's not a food. And similarly, the toothpaste is also in the complement of the drinks, because again, it is not a drink. Now, the other thing just to be wary of is, again, with this specific example, we have two sets, and the toothpaste happens to be in neither of them. However, based on our definition of the complement of a set is just things that aren't in it, I could now say the juice is in the complement of the set of food, because the juice is not in the set of food. So it belongs to the drinks, but at the same time, it's also in the complement of the food. Okay, so mathematically, getting that down, we write this using a superscript C next to our set. And again, as I've just mentioned, we say it's all the elements X, where X is just not in the set A. That's what it means to be in the complement. Now, an example with maths using actual numbers. If we take A to be the set of odd numbers, so 1, 3, 5, 7, continuing upwards, then the number 2 is in the complement of A, because 2 does not belong to the set of odd numbers. The final way that we can break sets down is using something called the set difference. Now, the set difference is very much like subtraction, and we write it as such. We write it as A minus C, and it's a very helpful way to think about what's actually happening here. So we have a larger set A, and what we're going to do is basically remove the subset C, and what we're left with is itself going to be a subset which we call the set difference. So what that's going to mean with symbols is that A minus C are just elements X, where those elements are in A, but they cannot be in C. So with my shopping, what that means is, we go back to the food, we have A, which is all of the food items, and then we had our subset C, which was the fruit, the banana and the apple. So if I remove the fruit from this original set, then what I'm left with, so the cookies, the chocolate, the tuna, and the chips, nearly said crisps, those 4 items are now in the set difference. So everything together is the food. That would be A. We have our subset C is the fruit. And the difference, A minus C, is exactly what remains behind. Now, an example again with some numbers. If we take C to be the set of odd numbers, so again, 1, 3, 5, 7, 9, carrying on, and then we have A as the larger set of all integers, then the number 2 is definitely in the integers. It's definitely an integer, so it belongs to A, satisfies this criteria here, but 2 is not an odd number. So we take the integers and we subtract or take the difference with the odd numbers, then 2 would remain behind in what is left. So that kind of brings us to the end of a quick-fire summary of all of the different types of sets, the properties of sets, and how those sets are related to one another. when comparing different sets, it's very... Apparently can't start any video, right? Try again. Take two. When comparing sets, it's helpful to have a way to visualize the relationships among them. Fortunately, we have the perfect tool in the form of Venn diagrams. Now, a Venn diagram, as laid out in front of me, is simply a series of overlapping hoops where each of those hoops represents a particular set. So here we have the hoop A, which is in green, is going to represent the food items. And then we have a second set B in the yellow hoop, which is going to represent drinks. Now again, I can take my shopping and begin to sort these items into their respective locations on the Venn diagram. So we have water, which is definitely a drink. We have some Coca-Cola, which is also a drink. We've got some cookies, that's going to be a food. Banana, I know that one's a food. Apple is going to be a food. We've got the chips, it's going in there. Juice, that's a drink. Tuna is a food. What have we got here? Ginger ale, that's a drink. Chocolate, that's a food. Okay, now we get to the toothpaste. Now the toothpaste is neither a food nor is it a drink. So what I'm going to do with the toothpaste to signify that it does not belong to either of the sets in front of me is I'm going to place it outside of both hoops. So the toothpaste is still in the universe of items from my shopping cart, so it goes on the table, it is still represented on the diagram, but importantly, because it is neither in the set of food or the set of drinks, it's going outside of those hoops. And the last item, the soup. Now soup, to me at least, is both a food and a drink. So I'm going to place the soup in that central section. So this is the intersection of our two sets. This is the overlapping region where the soup, you'll notice here, is both inside the green hoop, signifying that it is a food, belongs to set A, and it's also inside the yellow hoop, signifying that it is also a drink and belongs to set B. And if I were to take all of the items across both hoops, so across the green hoop and the yellow hoop, then we could say that the two hoops together, which we refer to as the union of those two sets, so A union B, we would say that that would be the set of edible items. And again, importantly, we know that the toothpaste is outside of that set of edible items. It's outside of the union. Now, just to make sure that we are clear on those definitions and visualizations, I have smaller versions over here on the screen. So I ended by talking about the union. So the union of the two sets, as we can see on the table, is just the collection of all of the drinks and at the same time also the collection of all of the food. So the union there, food, union, drink, would be all edible items. So anything inside those hoops. Then we looked at the intersection. The intersection here would be the central region, so it's in both the set A and the set B, and so that would be where the soup is positioned on the table. We also have the complement of a specific set. Now, I didn't refer to this one explicitly with those items, but what we can see here is that following our definition or recalling our definition of the complement, if an element is in the complement of A, it means it is not in the set A. So as we can see here in the shaded region, this is anything that is outside of the hoop A. So of course we include B, but we have to also exclude from the complement the bit in the middle, as anything that's in the overlap is definitely in the set A. And we can also see here that anything external to the hoops, so our toothpaste, once again, our toothpaste does belong to the complement of that set A. And finally, we have the set difference. So here, for example, if we wanted to do A minus B, so the larger set A of food items, but then we want to subtract or remove the drink items from the food, then what we're going to do is remove the overlapping piece in the middle. So A minus B in this context is going to be this section over here with just the food, but not the soup, because the soup belongs to B, and we have done A minus or A remove B. Now, forgot my transition line. OK, I'll just redo the transition to the final. So because the soup belongs to B, and we are doing A minus or A subtract B, then the soup is not in that set difference. So here we have a summary of all four of these Venn diagrams, these visualizations of these important set relationships. Now you'll notice, of course, that there are only two sets featured here. And that's really just because I can only fit two on my demo table. I would, however, like to show you what this looks like when you have three hoops, but for that I'm going to be a little bit more creative. As you can see, we have a rather exciting looking triple Venn diagram with 3 different sets, 3 different categories. And shortly, I will be attempting to place some emojis on that diagram. But first, let's just really unpack what a triple Venn diagram is displaying. So going over here to the screen, I've shown a diagram here of the 3 hoops, the 3 categories, which have been labeled A, B, and C. And just as before with the 2-hoop Venn diagram, the 2-set Venn diagram, each circle is representing belonging to set A, set B, or set C, and therefore those overlaps are going to tell you that an element in one of the overlapping regions is belonging to more than one set. So if we focus first on the one at the top, so this region here, we can see that this is inside our region A, it's inside the set A, and it's also inside the set B. So this is going to be the intersection of A and B, and this top section is not in C, so we're outside of C. So here we would say this is just an element that is in both A and B, so this is the intersection A intersect B. Now, due to the symmetry of the diagram, we're going to have similar relationships in these other lower sections. So if we go down here, this one to the bottom left, again, we are inside the set of A. We are also inside the set of C. So this region is going to be the overlap of A and C, which we represent as A intersect C. So both A and C are true. And then that leaves the final region over this side, which again is inside our hoop B. It's inside our hoop C, so it's going to be B intersect C. And now what we're left with is the central region. Now, the central region, if we imagine placing something here, we're inside the set A, we're also inside the set B, and we're inside the set C. So this is our first new type of set, because we now have A intersect B intersect C. So the rules are the same, follows the same principles as A intersect B, but now 3 separate things must all be true. We must have A being true, B being true, and C being true. So, armed with this new information, this understanding of the triple Venn diagram, let's see if I can place my emojis on the board. So the first one I have here is a vampire. So we have a vampire emoji, which needs to be placed somewhere in these categories. So let's look at them one by one. So vampire, does a vampire only come out at night? Pretty true fact about vampires, right? They do not like sunlight. So I think the vampire is definitely somewhere in this circle. But vampires are also immortal. Again, one of the defining characteristics of a vampire is being immortal. Do they enter people's homes? Doesn't feel like that's one of their main traits. So I'm tempted to say the vampire, it only comes out at night and is immortal. So both of those properties are true. So I'm going to place the vampire there in the intersection between those 2 sets. OK, what have we got next? OK, this is a good one. We've got a cockroach, a terrifying looking creature. So a cockroach, right? Again, let's think through our categorizations, our sets. Does a cockroach only come out at night? I do believe they are nocturnal. So I think, again, we're working on this side of the diagram. They feel like they're immortal, but they're definitely not. They are a real biological creature. So they cannot be in the immortal set. And they definitely enter people's homes, right? Ideally, we don't want them to, but being cockroaches, they find a way. So I think our cockroach is going to go over here. So the cockroach, just to clarify that, it only comes out at night, and it enters your home, unfortunately. OK, where are we going next? Ooh, we've got a zombie. OK, so a zombie. Right, so zombies they're going to be immortal, right? Sort of they are the undead. By definition, so the zombie is going to be an immortal, have the characteristic of being immortal. And coming out at night, I've seen far too many movies and TV shows where zombies are around in the day, so I don't think that is true. So we need to be outside of that one. And they do enter people's homes, unfortunately. So I think, again, for the zombie, we're going immortal and enters people's homes. So hopefully, if this has worked, I have one remaining emoji, and I'm hoping that this is going to fit in that central region. So I need something that only comes out at night, is also immortal, and enters people's homes. I've got just the character. It could only be Santa Claus, Father Christmas himself. Only comes out at night, delivers your presents overnight, definitely immortal, has been around forever, and definitely is entering people's homes through the chimney. So Santa himself is going to fill in that final position on our triple Venn diagram. So to summarize, we've talked through how Venn diagrams are both an incredibly helpful way to visualize the relationships between sets, but also, as we've just seen, a great way to understand memes. when working with, it's always the voice, working. When working with combinations of sets, for example, the union of two sets where we've added them together to build something new, or perhaps the intersection of two sets where we've looked at the overlap between them, or maybe the complement where we want everything outside of the set. It's helpful to be able to combine these operations. So perhaps we're interested in the complement of the intersection, or the complement of the union, or the union of the intersection. So this can quickly escalate, but there are some very important laws and rules that we want to follow when working with combinations of these set operators. So one of the most important set of laws or rules that we want to be aware of and want to be capable of using is a set of laws called De Morgan's laws. Now these tell us how to use complement, or how to apply the complement of a set when we have an intersection and when we have a union. So the first law here is saying that when you have A intersect B, so the overlap of A and B, and you want the complement of that, it's telling us, well, that's actually the same as the union of the individual complements. And the second law is telling us the complement of the union is the intersection of those individual complements. So there's a nice symmetry to these laws, which helps with remembering them. Now I'm going to pop over to the board, and we're going to look visually at what is happening in this first of De Morgan's laws. So we will use our tools of Venn diagrams to help us to visualize this. And we're interested in two sets. So we have our universe given by the rectangle here. And then if we draw the two sets A and B, so we have A, and then we have the set B. I will just label these. Now, the first of De Morgan's laws tells us that A intersect B, taking the complement of that, is equal to A complement union B complement. So what we would like to do to try and get a visual proof, shall we say, of this result is to draw on one diagram the left-hand side of our equation. So we will draw this one up here, and then I will draw a second diagram, which will be the right-hand side of our equation, and hopefully they will look the same. So this one will go down here, and again, we will need those two circles representing A and B. So we will begin with the left-hand side, the top diagram. So we want the complement of the intersection. So if we think about, well, what is the intersection? The intersection of A and B is going to be the overlapping region. And then the complement is going to be everything outside of that. So really all we have here is just everything that is not in the overlap. So it's going to take a lot of shading. It's going to be all the way around here, going right across both A and B, but carefully avoiding that overlap, that intersection in the middle. So that entire region is all shaded out. And what we're left with, and I'll just highlight this to really emphasize it, is just this piece in the middle. Okay, now the second one, the right-hand side of De Morgan's law. So this tells us that we want to take the union of A complement alongside or with B complement. So we'll start with A complement. So that just means everything outside of the set A. So again, that's going to be quite a lot of the diagram. So we're going to be anything that's outside of A is going to be shaded in to give us A complement. So of course I'm going here right through the set B as well, but being careful that the intersection is included in A, because anything in A and B is still in A. So that gives us the first term, the A complement, and then we want to take the union with B complement. So B complement, again, following the definition, is everything outside of the set B. So if I try and do this with an opposite shading, we want to mark out A, but importantly leave behind B. So we're going to cross off all of this. This is all in B complement. again, B complement just means not inside B. So we shade out all of this. Now, there's quite a lot happening on the diagram. You'll notice some regions are double shaded, some of them are single shaded, but all we're interested in is the parts that are not shaded. And once again, we can see the central piece here is, in fact, the only part remaining unshaded, and so we can see that both Venn diagrams are the same, thus providing a nice visualization of the first of De Morgan's laws. Now, as well as De Morgan's laws, which use complement alongside the union and the intersection, we can also combine the unions and intersections themselves. And these are referred to as the distributive laws. Now, some of you may recall the term distributive when thinking about numbers and how we add and multiply numbers using brackets, and they behave in a very similar way. So we now need 3 sets in order to be able to have multiple operations occurring between them. So the distributive laws tell us that when we have the intersection of a set A with a union, then that is the same as the first intersection union the second intersection. And then the second of the distributive laws tells us that A union the intersection of the other two is the same as A union B intersected with A union C. But once again, I think seeing these visually is actually the most helpful way to see what's happening and why these laws are true. So let's have a look at that first one. So this time I'm going to have to really test my drawing skills and try and draw 3 Venn diagrams. So I'll begin by writing out the formula that we want to show. So we want to show the first distributive law, which is that A intersect B union C is equal to A intersect B, and then we take the union of that with A intersect C. Okay, so if I now draw out, we'll proceed as before. We will draw 2 diagrams where the first one will represent the left-hand side of the equation, and this time, of course, we need 3 overlapping sets on our Venn diagram. So we are interested now in the intersection of A with B union C. So it would help if I had some labels, A, B, and C. Okay, so B union C just means anything inside B or C. So anywhere in the hoop B and anywhere in the hoop for C. And then we want that parts of those hoops that are also in A. So that's going to be anything up here. So this is in B and A. The central piece happens to be in A, B, and C, but it's definitely in the intersection of A and B or C. But we also get this section here. So B union C is going to be the 2 hoops, anything in B and anything in C. And then when we intersect that with A, we get those 3 regions. Now for the right-hand side, again, we begin with the same rectangular drawing, and I'm going to add in my 3 hoops and label those A, B, and C. And now let's think about the union that we want in this situation. So here we want A intersect B. So let's draw that one first. So A intersect B is just the overlap between A and B, and of course that will include that central piece. So the very center also is in C, but it still is in both A and B, so we must remember to include it. And then we also want the union of this intersection with A intersect C. So A intersect C is the overlap between A and C, which is going to be this region. And again, we can see there we end up with some parts that are double shaded, but it doesn't actually matter. We're just trying to show that the shaded regions are the same, the diagrams are the same, and once again, we've got a nice visual proof of those distributive laws, or at least of the first distributive law. So there are many other ways that you can combine sets. You can begin to add more sets. Perhaps we have a set D, a set E, and you can begin to include other combinations of intersection, union, and complement, but the ones that I've just mentioned today are the most important. When working with a set, perhaps of objects or perhaps a set of data, it's usually helpful to think about the size of that set, especially if we want to compare different sized sets. Now, fortunately, the definition of the size of a set is exactly what you might expect. We define the size of a set to simply be the number of objects in that set. And we denote this with two vertical lines written here either side of our set A. For an example, here is a collection of names, some of which you may recognize. And in our set A, we have Tom, David, Brian, Carter, and Colton. So there are 5 elements in our set. So we would just say the size of the set A is equal to 5. Now, of course, some sets can be infinite, which means we cannot list out all of the elements and then close off the set nicely. So in this instance, we simply say the set has an infinite size. Now, an example might be something like the set of integers. So even though I know all of the integers, we cannot actually close. Sorry, I'm getting into stuff that I don't want to get into. When working with a set of objects, or perhaps a set of data, it's usually very helpful to think about the size of that set, particularly if you're comparing 2 or more different sized sets. Now, fortunately, the definition of the size of a set is exactly what we would hope it would be, and that is the number of objects in that set. So formally, we say the size of a set is the number of objects in the set, and we denote this with 2 vertical lines either side of the name of our set. So here, for the set A, we just write these 2 vertical lines either side of the A to denote the size of A. So if we have an example here of a set containing some names, which you may recognize. So we have Tom, David, Brian, Carter, and Colton. So there we've got 5 elements in that set, so we would just say the size of A is equal to 5. Now, sometimes we may have an infinite set, and in that situation, we simply say the set has an infinite size. So for an example, we might take the set of integers, all of the positive and negative whole numbers. That would be an example of an infinite sized set. Now, when working with combinations of sets, how do the sizes interact? Is a very interesting question. And one of the ways that we understand this, or the best way to understand this, is using something called the inclusion-exclusion principle. So for 2 sets, it tells us the following, that the size of A union B, so recall that A union B means A or B together, so the 2 sets sort of meshed into one. And if we wanted to look at the size of those 2, then what we do is we count all of the elements in A, and then we count all of the elements in B, and then we take away the elements that are in both A and B. So we take away the size of the intersection. Now, to see really where this is coming from, it's very helpful to draw a diagram, so that's what we're going to do. So we'll go back over to our surface, and we're going to look now at a Venn diagram of this situation where we want to work out the size or count the elements in A union B. So if we have our Venn diagram as follows, we have A and we have B, and I will put some labels on these. And we're interested in counting all elements, so we want the size of A union B. So according to the inclusion-exclusion principle, it says one way to do this is to count everything in A. So let's shade in all of those elements that would be counted. So let's count everything in A as the first part of our formula. So we count everything in here, and of course the overlap in the middle does belong to the set A, so we would be counting everything in there. Then it tells us to count everything in B. So we add on the size of B. So that means counting all of these elements, everything that is inside the circle here that represents the set B. And now, looking at the diagram, we can see that what's happened here is we counted everything in A, we counted everything in B, but we've actually double counted. So we can see this with the two directions there in the shading in that central region. But the central region, we know, is the intersection. So therefore, if we take away the size of the intersection, then that removes one of those double counts. We're left with a single count, and then we can see we have counted everything in A, everything in B, and we have indeed counted all of the elements that's in the union of A and B. Now, we can actually generalize this principle beyond just two sets. And doing so, we can then, for example, look at what happens with three sets, three hoops on our Venn diagram. So here I've just labeled the regions. So recall that we have the double intersections, and then the central piece is going to be our triple intersection of all three sets. So if we try and follow a similar approach, let's think about what was the actual methodology of counting the size of the union. So we want to count A union B union C. We want the size of that triple intersection, that triple union. So we might begin by counting everything in A. So if we count everything in A, we've counted everything here. Now we would count everything in B. So we would count everything over here. And we can already see there is some overlap between those elements. We've double counted some elements. And now if we count everything in C, we've again got some double overlap, but we've also got a triple overlap. So these single or double, let me say that again. OK, so I'll just go from we've also got a triple overlap. That work?
You got it.
OK, sorry. OK, we've also got, so we've also got a triple overlap in the center, and so we've actually counted, no, I didn't say that, did I? I tell you what, let's, it's okay, should I just, I did this, I'll walk back from the surface, I'll just go from there.
Fantastic.
I'll just go from the surface, yeah, all right. OK, so we had that. I just talked through the visual of inclusion principle, inclusion for two, and then I'll just say, right, so we can now generalize. OK, cool. I'm good whenever.
All right, ready in 5, 4, 3.
So the version of inclusion exclusion that we have just done a visual proof for was looking at the interaction between two sets, the union of A and B. But we can actually generalize this result for a larger number of sets. So if we look here at the Venn diagram for three sets overlapping, so we have A, B, and C, and now perhaps we would like to count or work out the size of A union B union C. So we're interested in all three of them together. Then we can just follow the methodology of what we saw for inclusion-exclusion on the two-set example. So if we think about what did we do first, we simply began by counting everything in A. So at this point, it's fine. Nothing has been counted more than once. Now we could go over and count everything in B. Now by counting everything in B, some of these regions, this overlapping region in particular, has now been double counted. So we just kind of make a mental note of that. And then we would add on everything the size of C, add on everything that's in C. So now we've got the size of A plus the size of B plus the size of C, but anything that is an intersection between two sets, so anything that's got a single intersection symbol, has actually been double counted. So we actually kind of need to remove one of those. We need to remove this, and we need to remove this one. But we've actually then, if we remove all three, the central part was triple counted, and then we've just removed it 3 times when removing the double counts. So at the end, we actually have to add back in the triple count. So it makes a bit more sense when you see the formula. So what we've got for the triple inclusion-exclusion principle formula, A union B union C, is you count everything in A, you then add on the size of B, add on the size of C. We take away all of the 3 single intersections. So A and B, A and C, B and C, we take all of those away, but we've now removed too many times the central piece. We counted the central part 3 times, we've now removed it 3 times, so we have to add back in the triple intersection. And this is why it's called inclusion-exclusion, because we are including all of the singles, we then exclude, subtract the doubles, and then we include again the triples. And this generalizes to higher and higher numbers of sets. Now, the 2 set one is probably the most common and the most important one to be comfortable working with. However, the 3 set one does allow you to solve some fun problems. And I'm going to end by sharing with you one of my favorite problems about fans of sports teams. So the puzzle goes as follows. In a class of 30 students, we know that everyone in the class supports at least one of 3 sports teams. So everyone has at least one team that they follow. They could, of course, follow 2 or 3 of those teams. Now, we all want to know who are those teams. So the first team that people may follow is going to be Golden State, the Golden State Warriors NBA basketball team. And they have a total of 16 followers. The second team of which people may be a follower is going to be Real Madrid, the football, as I would say, or the soccer team, Real Madrid from Spain. Lovely shirt for you here. And the Real Madrid has a total of 17 followers. And then our third team is going to be the Seattle Mariners, who have a total of 14 followers, who are, of course, a baseball team based over in Seattle. So we have 3 sports teams, and we know in total how many of our 30 students follow Golden State, how many follow Real Madrid, and how many follow Seattle. We also know some of them follow more than one team. So we have additional information. We know that 8 support Golden State and Real Madrid. We know that 7 support Golden State and Seattle. And we know that 9 support both Real Madrid and Seattle. And the question we'd like to know is how many support all 3 sports teams? In our class of 30, how many people are fans of all 3, Golden State, Real Madrid, and the Seattle Mariners? Now, this feels like a lot of information, and it feels like quite a complex problem. There's a lot going on here. But using the triple inclusion-exclusion formula, we can get to the answer actually pretty quickly. So let's do exactly that. So we will begin by writing out our formula that's going to get us to the solution. So what we know is that the size of all 3 together, so A union B union C, the size of that, we do the size of A, we then add on, so these are the includes, B and C. We then do the excludes, so we take away all of the doubles, so that's going to be A and B. We're going to take away the size of A and C, and we're going to take away the size of B and C. And then finally, we have to include again that final triple intersection. Now, we want to label which team is which. So let's just say A can be Golden State, B can be Real Madrid, and let's suppose that C is then Seattle. Okay, now based on the information given to us in the puzzle, we have quite a lot. So we know that in total, A union B union C, we know that that has to be 30, because the problem tells us that we have 30 students in the class and all of them support at least one team. So that means all of them are inside a hoop somewhere. So we know that 30 is the term on the left-hand side. Now, we're told the total number of followers for each team. So we know that Golden State has 16 followers. We know that Real Madrid has 17 followers. And finally, we know that Seattle has 14 followers. So that's just the size of A, the size of B, the size of C. Then we were told the number of students that support multiple 2 teams. So we were told that 8 support Golden State and Real Madrid. So we take away 8. We were told that 7 support Golden State and Seattle, and 9 support the final pair of Seattle and Real Madrid. So we take away all of those double overlaps. And then the final one that we don't know, right? We were asked to work out how many people support all 3, which is A intersect B intersect C, which is Golden State and Real Madrid and Seattle. We don't know that. So that is our X. So again, we've now got a pretty straightforward expression. We've just got some numbers. We can figure out the algebra, which I'll leave you to do for yourselves. Just tidy that up, add and subtract those numbers, and you'll find that the answer is in fact 7. So that seemingly complicated problem with all of these moving parts was actually reasonably straightforward, provided, of course, we had that inclusion-exclusion formula. OK, so what have we talked about today? We started by looking at the size of a set. We started by looking at, for a set with a finite number of elements, saying that the size is simply the number of elements in the set. But be careful that some sets can be infinite, and we just say they have an infinite size. And then we looked at these relationships between unions and intersections and how we can use the inclusion-exclusion formula to be able to count all of those overlaps and solve fun problems involving sports teams. So we have our universe of all possible things given by this rectangle here.
Great. Just give me maybe two more.
Yep. Okay, so we have our universe of all possible things given by this rectangle here.
All right, one more.
So we have our universe of all possible things given by this rectangle here.
Fantastic. And why don't you just clear that, and then we'll get set up for your recap again?
Yep. So I've just said some stuff, blah, 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 and I've just finished by saying, okay, so in summary, we looked at, in summary, we've defined, we now know how to work out the size of a set. So in summary, we define the size of a set. We now know how to work it out. So in summary, okay. All right.
All right, I'll count you in. And so you picked up with so. So
Yep.
So what have we?
So in summary,
around the podium there.
yeah, and then walk to the front. Gotcha, yeah. So in summary, we've talked about.
All right, here we go in 5, 4, 3.
So in summary, we've looked at how to define the size of a set and also how we could use the incredibly useful inclusion-exclusion formula when working with unions and intersections. In this chapter, we've learned that a set is simply a collection of objects that share a certain property. We've looked at how those sets might interact and perhaps overlap through the intersection, how we can add them together and combine them using the union. We also looked at how we could break down sets through subsets, supersets, and the set difference. We then looked at how to visualize all of these relationships using Venn diagrams. And finally, we talked about the size of a set and the incredibly useful counting formula in the form of the inclusion-exclusion principle. So now that we have the definition of a set, it would be helpful to start asking questions about those sets. And for that, we're going to need logic. Fortunately, that's exactly where we're going in Chapter 3. Hello world and hello maths fans. Today we are talking about sets. When working with data, we tend to group it into categories. Start again. So that first sentence, when working with data. Hello world and hello maths fans. Today we are talking about sets. When working with data, we usually group it into, I keep saying the wrong word, I'm sorry. Ay, 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 ay. Hello world and hello maths fans. Today we are learning about sets. When working with data, we usually divide it up to make it more manageable and to help us to spot patterns. So for those of you watching this video, we might group you according to your nationality or perhaps according to your previous experience learning mathematics. These groupings or categories we refer to mathematically as sets. In this chapter, we will begin with a definition of a set. We will then look at relationships among sets in the form of unions and intersections. We will look at sets within sets in the form of subsets and supersets, and we will also break sets apart using the set difference. We'll then visualize all of these different relationships using Venn diagrams, and we will end with a discussion about the size of a set and how we might generalize that to counting larger and larger combinations. And if everything goes to plan, by the end of this chapter, you will belong to the set of students that understand sets.